So our next lecture is on exponential functions. Let's start out with an example where we have f of x is 3 to the x and g of x is 1/2 to the x. So exponential functions are of the form a base number, non-zero, raised to power of x, which is different from polynomials, right? So polynomial, just thinking of an example that you could compare this to, x cubed would be a polynomial, but 3 to the x is an exponential function. Okay, so let's evaluate these functions similar to function evaluation that we've already seen before. So f of 0, we would just plug in 0 wherever we see an x. So this would be 3 to the 0. And the convention here is that if you take any real number that's non-zero and you raise it to the 0th power, then this is actually 1. So that's f of 0. So what would g to the negative 4 be? So g of x is 1/2 to the x. So we will just take 1/2 and raise that to the negative 4. And now we can use any property that we know about exponents to simplify this. So one of them that you could use right away, there's a bunch of different ways that you could simplify this. One way is you could bring this negative 4 into the numerator and denominator, but what do we know if we take a negative power? Well, that's actually going to make the reciprocal. So if I get rid of that negative, I can just flip the fraction that I have. So 2 over 1 to the positive 4th, right? That's just remember that if you have something to the negative power, that you will just take the reciprocal of it. And so now I just have 2 to the 4, and that is 16, right? So that's one way to do it. Solution 2, you could take this and write this to the negative 4, 2 to the negative 4, and then 1 to the negative 4 is the same as 1 over 1 to the 4, and this is 1 over 2 to the 4, and 1 to the 4 is 1, and 1 over 2 to the 4 is 1 to the 4 over 2 to the 4. This is getting a little bit tedious, but you have 1 over 16. So the reciprocal, 16 is 16. So see, this is a little bit less clear to follow, and it's best to just get rid of that negative if you can immediately, so you don't over confuse things. Okay, what about f of negative 1? Well, f was 3 to the x, so that'll be 3 to the negative 1. And we have a negative here, so that's going to be the reciprocal. So we have 1 over 3 to the 1, which is just 1/3. Okay, so yeah. F of 2 minus g of negative 2. So first of all, what is f of 2? Let's write that out. So f of 2 is 3 squared. And then what is g of negative 2? Well, g of x was 1/2 to the x, so this will be 1/2 to the negative 2. So then this will be 9 minus, and then that negative will take the reciprocal, 2 squared. So this is 9 minus 4, which is 5. Okay, moving on. How do we graph exponential functions? Well, one way to proceed, it's very similar to how we graph functions all along. We could make a table, right? So we can make a table of x values, and we can make a table for our y coordinates, which are our f of x coordinates, which is defined as 2 to the negative x. So now we just have to pick some inputs, and then we'll plot the points that we get. So what are some good inputs that are easier to figure out the outputs for? So let's see what happens if I plug in negative 1, if we plug in 0, and if we plug in 1. Okay, so if I plug in negative 1, then you have 2 to the negative 1, right? And that's actually 2 to the 1, which is 2. So we have a point at negative 1, 2. So we get a point, negative 1, 2. So we'll plot the following points. So if this is negative 1, and this is 2, negative 1, 2 would be about there. If I plug in 0, then I have 2 to the negative 0, so that's 2 to the 0, and 2 to the 0 is 1 by convention. So that'll give us the point 0, 1, so 0, 1. Now, if you actually think about this, no matter what the base is, if I were to plug in 0, it would be 1. Okay, so that's going to be a very common point that you plot for a lot of exponential functions. And then what happens if we plug in 1? So 2 to the negative 1 is, we have to take the reciprocal, so this is 1/2. So then we get a point 1 and 1/2. So 1 and 1/2. And if you want, you could continue this trend, but look at what actually happens. So negative 2, this will be 1 over 2 squared, so that's 1 over 4. So we're getting 2 and 1/4. You see that as you get larger and larger x values, it's getting closer and closer to 0. So that's exactly what's going to happen. Exponential function, at least in this situation, this exponential function is quite different because it's actually decreasing. I'm gonna give you another example where you have a positive base and you have the x is just a positive x, and you'll see that that's growing. So so this one's quite interesting just because you kind of get this picture here. So exponential function, there's the graph of this one, 2 to the negative x. Okay. This is an example of what's called exponential decay. So we actually see that the values are decreasing as x increases. And there are many natural phenomena that behave like this. But let's move to the next example, and let's graph f of x equals e to the x. Now, e is a very special value. This is approximately 2.71828. It's a transcendental number. It's similar in importance to pi, but pi is a very geometric number. E comes up in several contexts, but it's really defined naturally through calculus. But it's a very important base, as we'll see in an application very soon, and it'll come up in compounding interest. Okay, so it looks kind of bizarre to use this as a base, but you'll see that the graph, we're gonna try to graph this. The graph of this is very similar to the graph for, say, 2 to the x or 3 to the x, and I encourage you to actually plot all three of those maybe on the same graph, and you can kind of see the difference in behavior of all three if you were to be very careful on how you plot those points. But we could proceed in a very similar way. We could set up a table, right? And remember, you have a scientific calculator, so you can plug in these values and get your approximations, okay? But right now, you can kind of just think of e as a number that's between 2 and 3. But it happens to have fundamental importance. And you know what? I'll point something out in the graph actually a little bit. So let's make a table. So x and our y coordinates, f of x is e to the x, and we'll plug in similar points. So if I plug in -1, 0, 1, what happens? So if I plug in -1, then I get e to the -1. Well, that's 1 over e. And I mean, if you didn't have a calculator, you can approximately see that that's like 1 over 2.7, right? So it's kind of like a half, but closer to a third, I guess. Okay, so a little bit smaller. Okay, so we could plot those points. You know what? Let's, just for the sake of doing this, if you take out your calculator and approximate this, sometimes you have an exponential button that will allow you to just put in the exponent here. And you just need to look for the e to the x button. There's usually an e to the x button, and if you punch that in, you can figure out what this is. And it looks like this is approximately 0.368. You know what? It's actually just better to go to 4 decimal places if you can. So 0.367, and then it's 87, so we'll round that up to 9. Okay, and look, it's just like what we said, right? It's between a third and a half approximately. So we can plot that over here. So come over here to -1. Did I write -1 up above? Yeah, -1. Okay, good. -1. And then we'll go up approximately a half, but a little bit less than that, right? So it'll be about right there. Okay, so that'll be your -1, and then 1 over e. If we plug in 0, that'll actually be easy because any non-zero real raised to the 0, that's a 1. So we're going to get the point 0, 1. So we have this point 0, 1. And then e to the 1, well, that's going to be e, and that's approximately 2.71828. Okay, so those are your coordinates, right? 1, and then e. So 1, and then if this is 2, and then that's 3, 2.71828 would approximately be here. So what's happening is as x gets more negative, it's actually getting closer to 0. And then it grows, and it grows very rapidly. Okay, so that's a sketch for e to the x. So that's good enough for graphing this. But okay, now another reason that e to the x is so fundamental, which we're not going to be able to get to in this course, but I will point out something geometrically interesting. Do you see that at this point, 0, 1, if you were to plot the line that just touches the curve right there, but it goes through that point, but it only touches the curve right there, you'd get what's called the tangent line, and the slope of that thing is 1. And e to the x is the special exponential function where that slope there happens to be 1. That's the only base that actually makes that correct slope. So this is another reason that it's of fundamental importance to calculus. But we'll see another example where e to the x actually shows up naturally. So here's a very interesting application of exponential functions. So these are compounding interest functions. Okay, so let me explain what each of these variables are. So compound interest. So we have this formula, which is actually a function of t. So a here, a is the amount after t years. Okay, so what you're going to do is, this is a function. It's like you start with a value. So this p here is the initial amount. Okay, so that's essentially how much you would invest. Okay, so let's say that an example that I'm sure many of you are encountering already. If you take out a loan, right, you are going to take out some initial amount, and then there is an interest rate on that loan. Okay, so what's going to happen is the amount that you will owe will be more than the amount that you initially took out. But if you were, say, investing the money as well, instead of taking out a loan, let's say you were going to put the money in some kind of investment that will grow, like a savings account, or maybe you were going to put this in the stock market or something like that and hopefully get some return, right? Then we have a nice formula for it. So all you got to do is you just take your initial amount and you're going to multiply by this factor here. And this factor, if it was a loan, it'd be nice if this actually was decreasing this. But if this is an investment, you want this to increase, right? You want the amount that you have to increase over time. So that would be the amount after t years. So what are the variables here? So t is the number of years. Okay. P is your initial amount, and A is the amount after t years. Hopefully I don't have to label those two again. But what's R? R is the interest rate. So let's just write that. Okay. And what is this n here? So n appears twice, appears down here in this fraction, and then up here in this exponent. So what's happening is when you make the investment, it's going to be compounded a certain number of times a year. Okay, so this is compounded n times a year. Okay, so let's say that it was compounded annually. Then n would be 1. It would be compounded once a year. If it was compounded monthly, then n would be 12, right? It would be compounded 12 times a year. Weekly, what would that be? 52, and so on. Daily, 365, and so on. Okay, so that's our description of the function, compound interest. We'll come back to this continuously compounded one, but this is interesting to note that e's here. So let's see how much of this we can answer with just this first formula here, a compound interest formula. So suppose that you deposit $500 in an account with an annual interest rate of 8% compounded monthly. All right, so that right there is telling you a lot of these variables already. So you see that you are depositing $500. That right there is going to be your P. That's going to be your initial amount, right? Into an account with an annual interest rate of 8%. So what is this 8% right here? That is your R, right? The interest rate. And now it's telling you that it's compounded monthly, and compounded monthly is giving you N, right? N would be 12 because you're going to compound that 12 times a year. Okay. Now, anything else we know right now? Well, we know the amount you're depositing, the interest rate, and how many times it's being compounded in a year. So at the moment, we just don't know what t is, right? But maybe that'll be part of the question. So find a function that gives the amount of money in the account after t years. All right, so that's actually just saying to literally just write this out, but substituting these things in. So that would be a of t is p 1 plus r over n n to the power of nt. So let's replace all these things. So this would be 500 times 1 plus r is 8%. So we have to convert 8% to a decimal value, right? Because you're not just going to put percentage there, but 8% is 0.08 divided by n, which is 12, and we will put that to the power of 12t. And that's our answer, right? So do you see at this point that the only thing that's unknown here is t, but as soon as I specify t, then it would give me this amount after t years. So that is indeed a function of t. All right, and I would just leave it like that because right now we don't really have to simplify. But do you actually see that what you have here, this 1 plus 0.08 divided by 12, that's just a number that's a little bit more than 1, right? And if you were to not change the amount that you're, like if you just, like if you just put the $500 under your mattress, then it's not going to grow, right? It's just going to stay $500. So that wouldn't have this multiplication factor. The multiplication factor would just be 1. Right? So if the interest rate was 0, then you'd have 1 plus 0, which is 1, and 1 to any power is 1. So that would be sort of like the under the mattress interest rate, which would be the one you don't want to do, right? You want to invest it and make some money. So this will be a little bit more than 1, and then as this exponent increases, you'll get a multiplication factor here, and it will make this grow actually. Okay, so that's what's very neat about this. The other reason I would encourage you to kind of leave this alone is as soon as you start to round things, like if I actually write this out, it would be 1.006666 and 6. It just keeps repeating. As soon as you round that and you take these exponents, it's not going to be very accurate unless if you go out to very, very many decimal places. So I encourage you to kind of like leave that alone and do the math and then round afterwards. Okay, so let's see what the next question is. The next question is find the amount of money in the account after 5 years. Well, we have a formula for the amount. So all we got to do now is just plug in 5, right? That's 5 years. So all I have to do now is just plug in 5. So the answer is 500 times 1 plus 0.08 divided by 12 to the power of 12 times 5. Okay, so I would encourage you, if you're going to use a calculator to actually approximate this, but this is how you would write that in, right? 500, and then I would put parentheses here, and then put 1 plus 0.08 divided by 12, close parentheses, and then you will probably put like some kind of exponential button that you have. Usually it's x to the y, right? And then put this thing in parentheses as well, unless if you want to write that out as 60, which might be a good idea, just write that as 60. But just make sure that you're very careful when you're inputting all of these things. So take out your calculator now and see what you get as the answer for this. Okay, so after doing this, it looks like we are getting approximately 744.9, and since we're going up to cents, let's just round this to 92. It's 9228, so we'll round that to 92. So $744.92. You should also ask yourself, is that actually a reasonable answer? Okay, you're putting this into an account. You have $500, and 5 years later, you're only earning 8% on that. So if you're getting like double the amount or something, or maybe $1 million, then you made some error here. Is this reasonable? Could you go from $500 to $744 after 5 years with 8%? Well, that seems pretty reasonable, but the calculator actually verifies that it is. Okay, but just make sure you're checking this answer, because if you're getting something like $1 million, well, that'd be really nice if you could take $500 and turn it into $1 million after just 5 years of 8% compounded annually. Okay, so what's the next question? Next question says, how many years will it take for the account to contain $1,000? So the initial investment was $500, but we're trying to figure out how many years would it take. You're trying to figure out T, right? How many years? So in other words, right, already you're going to find T so that A of T, it'll take for the amount to be 1,000. Okay, find T so that this is true. Okay, well, what is A of T? We already have a formula for that, right? We have a formula right here. So we're setting this to equal to 1,000, and then we're going to solve for T. All right, so set those two equal. So this will be 500, 1 plus 0.08 divided by 12 to the power of 12t. Okay, now this right here, to actually solve this, we are going to need some more advanced knowledge. So this will come up again when we are actually solving exponential equations. So this is an exponential equation. And we'll see how to finish this in the end. Okay, so we're trying to figure out what t is. Okay, now solution 2, let me show you another way that we could do this. We will find the exact value later. So this is covered in 8.6 in your text. Okay, exponential equations. So we'll come back and solve something like that. Okay, but how could we get this another way? Well, you could sort of do some guessing and checking, right? So here's a solution 2. It's not going to give you the exact answer, but you could do some guess and check. Well, the previous one, after 5 years, you only have $744. So you know what? Let's just see how much we have in there after 6 years. So take out your calculator, see what you get after 6 years, after 7 years, after 8 years, 9 years, and just see what you get approximately for these, and see if they're getting closer and closer to 1,000. Well, after 6 years, it looks like it is approximately, let's just round this up, so 806.75. After 7 years, it looks like this is approximately 873.71. After, let's see here, after 8 years, looks like it is 946.23, and then after 9 years, it is 1,024.77. So how many years will it take for the account to contain $1,000? Well, it's between 8 and 9 years. So between 8 and 9 years. Okay, so you will need at least 9 years to get more than 1,000 if you wanted to answer it that way. But we could actually get the exact T. It'll probably be approximately 8.7 or so. So we can get the exact value. But that's how we can get this one right now, just by guessing and checking. That's perfectly fine. You have a calculator right now. Okay, but later I'm going to show you how to solve exponential equations. So that'll be a good one. All right, and then the last question is, if the interest were compounded continuously, how much money would the account have after 5 years? So that brings us to this other equation up here. So if you increase the number of times you're compounding this thing, okay, it's going to change this n value. And if you compound it continuously, that means you're letting the number of compoundings, you're letting that go to infinity. So if you do this every day, you're increasing n, right? That would be 365 times a year, but you could also compound it instead of daily. You can compound it hourly, and then minutely and secondly, and you can make that as small as you want. So you can that increment of time as small as you want, but you're making n go to infinity. And it turns out when you do this, you get a very interesting answer. In the end, if you let n go to infinity, you'll get this super simple version of what we're working with. The amount is just the initial amount times e, that special base that I was talking about before, 2.71828, to the RT. So it's funny. It sounds more complicated because you're compounding it continuously all the time, but the formula ends up being super nice. And this is actually one reason that a lot of places choose to compound continuously. All the mathematics is much easier to calculate. And actually, you benefit as the customer because you will get a better rate. You'll get more from your investment this way. Okay, so let's see what happens. So come down here. Let's try to write a formula exactly again, but with all this information, but compounded continuously. So a to the at is your initial amount, e to the rt, the rate times time. Okay, so you don't need an n here, which already makes it kind of nice. You just need the r. Okay, so what is this? The initial amount was $500 still, and then the interest rate was 8%. So that is the formula for the function, okay? And then how much will it contain after 5 years? We'll just plug in 5. So you're going to have to use your calculator to actually figure this out, but it's much easier to punch this into your calculator because you will just put this in parentheses when you punch this into your calculator, and you'll get a nice answer. So I'm getting 745.91. Okay, now if you compare that to compounding this monthly, same exact investment, right? But you're compounding it monthly versus continuously, what is the difference? So you see, you're only getting 744.92. I mean, it's just a little bit more, but you see the mathematics is actually just much simpler. I don't have to deal with this, okay? So yes, that special natural base E turns out to be of fundamental importance when you're doing compounding continuously. And the formula is quite nice. It's just you're making the weird part the fact that e is sort of this oddball number, this 2.71828. But it's in your calculators, okay, already as this natural exponential. And it's going to come up again and again and again in many, many courses.